Good evening. Welcome to the first installment of the OCTAVE Insight series. Apologies for the slight delay in starting. We were having to solve some technical issues. My name is Chamita Vanaguru, and I'll be your host for the evening. When I'm not hosting webinars, I work as an analytics delivery lead at OCTAVE. OCTAVE is a center of excellence for data and advanced analytics within the John Kearns Group. As a delivery lead, it is my responsibility to bring together the data scientists, the data engineers, the implementation experts, and the platform engineers to deliver successfully on our use cases to the different John Kearns businesses. When we started this OCTAVE Insight series, we wanted to create a platform where advanced analytics professionals such as yourselves can come together to share insights and experiences. With this in mind, we want to make this webinar to be as interactive as possible. So please, the question and answer feature is enabled. So please do send in your questions and share any experiences or insights that you may have. I will ensure to pick them up as appropriate during the course of the webinar. We also do have a gift lined up for you. Our friends at Microsoft have kindly offered to sponsor a giveaway for the webinar. All you have to do to win it is to answer two simple questions that I will put to you during the course of the webinar. At the end of the webinar, send in your answers to octave@keels.com. We will randomly choose the winner, and announce during our next webinar on the 1st of December. Today's webinar is about the evolution of data engineering over the last decade. Bhagya Reddy from Quantum Black was going to discuss this with me. Unfortunately, due to a family emergency, she's not able to join us this evening. However, I have someone equally capable and experienced, my friend Anshul Verma from McKinsey, where he works as a data and digital expert. So without much further ado, Anshul, over to you, buddy, to take the conversation forward.
Thank you, Chamita, and welcome all to this webinar. My name is Anshul Verma, and I'm a data engineer, a data architect, and I've been working in the field of data for about 15 years. Today, the objective of this webinar, this discussion really is to discuss on the evolution of data engineer over the last decade or so. And with the experience that I've gained as part of McKinsey over the last few years, working across sectors, across clients, working in building data assets, data platforms, I'd like to share that while we talk about the evolution of data engineering over this period. Looking forward to a discussion. Please feel free to actually post on your questions on the chat window, and Chamita, my friend, will actually bring this forward for our conversation. And I really hope that we can discuss and talk about a few important points that you can take away from this webinar and also learn while we are actually discussing. Talking about data engineering and the history of data engineering per se as a discipline has been there in existence for many decades already. About a few decades back, data engineering was specifically related to how data is available in a small system. Small data, you would remember about floppy drives that used to exist. That was also data, that was small data. And today we have big data, terabytes and petabytes of data, and distributed across the globe. The objective of data engineering has remained same. However, the scale and the way data engineering actually enables the insight generation out of data has actually been changing over the years. Over the last decade, and the last decade itself has been the decade where most of the changes within data engineering has happened. From actually acting as standalone systems where data used to be present in individual databases, where data engineers and other data specialists used to actually work on monoliths or specific standalone databases. We moved on to something called as an Hadoop era, where we actually started moving towards distributed computing. From distributed computing, we actually moved to an era of a cloud era where the philosophy of Hadoop actually continued, and we had a lot of power, a lot of compute, a lot of RAM, a lot of data all at our disposal to actually make sense of that data. and now we are actually moving ahead from the cloud era too, and looking forward to other endeavors and other horizons. However, if I take a step back here, data engineering as a discipline has been the core for enterprises to make sense of the data that they generate. Uh, about a decade back, 2 decades back, data was actually used just to understand how is the business running right now, how is the enterprise running right now, to get the transparency in forms of reports, standard reports that were created and made available to the business leaders to understand. From that era where actually data was used for very, very specific purposes to today where data is used for exploratory analytics, advanced analytics, for predictions, for prescriptions as well, to to a level of automation where hopefully in the near future human intervention and automation will human intervention will reduce, and automation will go to that extent that a lot of our decisions would be automated, and we as humans would be focusing on aspects of business decision making that are really core and requires thorough understanding, and all the repetitive tasks would be taken care by the algorithms themselves. From standardized reporting to actually this prescription-based analytics reporting, data engineering as a discipline has actually been enabling in every forefront. Organizations today have access to a lot of data, a lot of compute as well, a lot of RAM, a lot of code, a lot of libraries. You will hear this word a lot of times, and that is actually what this era today actually enables data engineers like you and me to make best use of the data. However, if we look 10 years, 20 years back, this capability, this accessibility of different tools, of different technologies, multiple choices of architectural patterns wasn't really there. There was data. The data as well was small, but over time, the three big V's of data: velocity, variety, and volume, that has changed dramatically and drastically, and it continues to do the same. Like I was calling out, we started from a standalone era, moved to a Hadoop era, where we actually embraced and adopted distributed computing to actually cloud computing, and now we are going beyond. Data engineering as a discipline has seen a lot of milestones. It has been enabling throughout every enterprise that's trying to, or that's aspiring to generate value from their own data, and it will continue to do so.
Thank you very much, Anshul. I think that was a very good high-level summary of how some of the tools and technologies involved in data engineering have changed over the last 10 years, right? Now, if I think back to when I first started my career, which was just under 10 years ago now, I initially started as a business intelligence developer, right? And you that role kind of required you to be more of a generalist, right? You had to do bits of ETL, database dimensional modeling, database design, visualization, a bit of data modeling, etc. Right? But now I see that the need with how some of these data engineering tools and technologies have changed, the skill set of a data engineer has kind of changed to a large extent too, right? And you're now required to be more of a specialist in that particular field. In terms of skill set, what would you say have changed over the last 10 years when it comes to data engineering?
Yeah, but when it comes to data engineering, and probably for other disciplines too, a lot of has changed, and a lot of has not changed as well. What has not changed are the basic foundational skills. As a data engineer, you need analytical skills, or this is a soft skill that you need as a data engineer to make sense of the data, how to structure the data, how to actually join two data points and really know what would be the output of that data, as an example, making sure that when you look at the data, you understand whether that data has a quality problem or not. That's more of an analytical skill when you are actually working with the data to understand how good or how bad the data is and whether you can make use of that data. That doesn't go anywhere. It was valid 10 years, 20 years back. It is valid today as well. Likewise, when we look at the technology front, ability to actually query the data. We used to use SQL, structured query language earlier. We use structured query language now as well. That doesn't change. And the bare minimum basic programming language that a data engineer would always need is SQL. However, over time, obviously, like you also pointed out, need of the hour also allows data engineers to adapt quickly, learn and unlearn quickly as well, and be proficient in additional tools. Programming actually has become a core and a central aspect of a data engineer's repertoire in today's day. Python actually has enabled a lot of data engineers across the globe to adopt data engineering practices. And Python is just one example of a programming language that different data engineers adopt. There are other languages too. However, if we look behind 20 years back and today, programming, engineering, or I should say software engineering with programming languages, that has become a core aspect of a data engineer's work too. You also called out about data modeling. That was relevant earlier. It is relevant right now too. Earlier, it was standalone systems where we used to work on single monolith systems. Now we are working on distributed computing. So understanding of how distributed computing works allows you to write better code. So those aspects of engineering have also started coming out, and data engineers at the heart are engineers only, and they need to know how things work because they are the ones who create these data assets. They are the ones who actually make sense of the huge volumes of the data as well. So some foundational skills have remained same. New skills have actually emerged, and data engineers have also adopted them wholeheartedly.
Yeah, no, thank you, Anshu. Yeah, we've got a question come in. How to start the career as a data engineer? What is the entry level qualification required? I think it'd be great if you can look at this question from both angles, right? What it is now and how that actually has changed over time. I think you kind of answered part of it previously, but it'd be good if you can delve a little bit more into it.
Yeah, for budding data engineers, the foundational skills that are called out, having an analytical or a soft skill to understand the data itself, and then having technical skills, and bare minimum is SQL to learn, and then at this era as well, having some bit of programming experience really helps getting started in the data engineering field. Also, what helps when you start in the data engineering field is to understand that when we look at data, working with data is a team sport. It's not an individual sport. Understanding what are the other disciplines of data, from data governance to data science, even business, how they get involved in the data, understanding the full big picture, and understanding that in that big picture, where do data engineers actually add value and add core part, allows you to also understand how you are adding value to the work that you are doing, and then adopting both the soft skills and the technical skills will make sure that you don't just start in your journey on data engineering, but also have a clear vision on where you are going, where you are adding value, while you continue to learn more tools, learn more technologies, and learn more engineering practices as well as you grow in your career.
Yeah, no, yeah, completely agree. I think, in the past, data engineering was kind of looked as not necessarily one of those general software engineering fields, right? But it's certainly coming to that point where actually, data engineering sits alongside any stream or any trend of software development, right? Because a lot of the features around even code deployment, like CI/CD, how you structure teams, how you run Scrum meetings, all of that is kind of now taken on board into the field of data engineering too, right? So I think that certainly is something that's key. Let's talk about, it's difficult to talk about data engineering without mentioning Python, right? How do you, what makes you think that, why has Python become sort of like the de facto language for us data engineers now?
Yeah. Python, like I said, for a data engineer, by the way, learning programming, and having programming skills is important. And Python just makes it easy to get started on that. And that's by the virtue of the language itself. The language itself is fairly easy. There are tons and tons of tutorials and help available publicly. There are a lot of tutorials available. It is also a general purpose language. Once you learn Python and you gain expertise in data engineering, as an example, you can also start using Python for a lot of other aspects of the work that you're doing as well. And as an example, while you use Python to build data pipelines, you can also use Python to actually build applications of front ends. You can actually use Python to automate mundane activities. You can use Python to build libraries as well. So just by the nature of it, the language is multi-purpose. It's easier to get started with, and because in this era today, programming is one of the expertise that data engineers should have. Python becomes a natural choice. This gets combined with a lot of tools and products in the market who provide support of Python as, in fact, I should call as first-class support for Python as compared to other languages. Again, just pushes different developers or data engineers really to adopt Python first and then probably other languages. This isn't to me, I should also call this out that Python being one of the primary languages, we pick that up. However, as data engineers, we should not really restrict ourselves to one language itself. And over the course of the next 30-40 minutes, I'll also talk about the importance of identifying the right tools, right languages for the right problem that you have at hand. And thereby you will also understand, and I hope that with my experience, you'll also agree with this point that the core skill really is programming, and Python just naturally becomes part of your repertoire. However, you do not restrict yourself to one language. Sharing just my own experience as well, I am proficient in at least 4 different languages, and one of them, by the way, is Bash and Awk, and a few of our traditional data engineers would relate with me that when we used to work with data earlier, Bash, Awk, Sed, these were the command lines, one-liners, and programs that we used to write to make sense of the data. And to this date as well, it's really important. That combined with Python allows me to program. That combines with Scala allows me to use certain platforms and tools. And that combined with R allows me to just extend my expertise in other verticals of data as well. So just giving that example to show that programming is the base skill. Python becomes a natural choice because of the virtue of how the language itself is. And then you actually, as a data engineer, expand your repertoire.
Yeah, no, I think, my takeaway from that is that it's important to understand and appreciate the principles of programming, right? And I think if you have a solid foundation in how to work with data, have a good understanding of how to work with data, how to merge, how to clean data, then understanding and learning a new language becomes a lot more simplified, especially when it comes to actually using that language for working with data. So I think the key takeaway for me would be that you actually, rather than concentrating on a language, albeit Python is certainly what you should get trained up now on, but it's also important not to kind of diminish the principles behind it and the principles of programming.
Absolutely.
As we talk about Python, another technology that has been key to data engineering certainly now is Spark, right? They've certainly done a lot of good things with it. The fact that it was first available as open source, there's a large community backing behind it. You have the enterprise version of it in Databricks, etc. So there's a lot going for it. But Anshul, in your mind, is it here to stay, or is it going to be replaced by a new technology in the horizon?
Well, it's here to stay. However, with every technology, and I'll probably Hadoop is case in point, by the way, that every technology has its time. It is here to stay for a while, if I have to just qualify that part as well. Over time, products themselves reinvent themselves, new features come in, and with the need of the hour, with the problems with current set of tools, if a product keeps on reinventing itself, and by the way, Spark and Databricks has done that, at least as of now, and they have been actually extending, and that's why I say they are here to stay. However, if we just look at our past, we'll also be able to understand how the future would look like. In 2006, somewhere around that, a paper from Google actually came out that was on distributed computing. Doug Cutting, a Google employee, actually used that to build a framework called Hadoop. And from that time, the concept of distributed computing actually became prominent and took prominence as well. And that is when that is when the era of distributed computing really actually started. However, that philosophy of distributed computing actually got embedded into a product called Hadoop. That Hadoop had its run for 5, 7 years, 10 years, in fact, and even right now, a lot of organizations are working with Hadoop-based systems. However, a lot of organizations are also moving towards cloud, and they're adopting cloud wholeheartedly. Some of them are using Hadoop on cloud, and some of them are actually just moving away from Hadoop and relying on cloud services. The reason I bring this point is that every technology has its time. However, the philosophy that these technologies are actually built across. Hadoop was built across the philosophy of distributed computing using cheap storage, identifying and working with multiple fit for purpose services or fit for purposes tools, connecting them together to solve a problem. That was the philosophy behind Hadoop, which was adopted by cloud. And right now, cloud has actually perfected and actually solved those problems. Likewise, Spark was born out of the need to solve the problems with MapReduce, which was the core part of Hadoop. MapReduce was slow when it was actually being used in an iterative fashion. Spark solved it by actually doing this MapReduce activity not on disk but on memory, and thereby immediately solving the problem of performance that was there with MapReduce based systems. Over time, Hadoop has also tried to cope up, but Spark has not stayed there. Like you also called out, Spark actually has a huge community support, a lot of features, and with a company like Databricks backing it, a lot of awesome features are also coming over time within Spark itself, thereby allowing them to reinvent themselves and being relevant in this age of technology, when every developer, every data engineer, even the data scientist, we have a lot of choice in terms of compute, in terms of languages, in terms of libraries. And until unless a particular product is relevant to the needs of the hour, it won't remain relevant very long. And Spark and Databricks, at least as of now, has been actually doing that, and it is being adopted by a lot of organizations as we speak too.
So you mentioned cloud, Anshu. If we actually consider cloud platforms, right? How much of the evolution of data engineering do you think has been driven by the spread of cloud platforms and the popularity of cloud platforms?
Well, quite a lot. It's also a matter of being at the right time being at the right place at the right time. Data engineering has been a discipline for decades and decades, and like I was articulating that within the existence of data engineering, there have been multiple eras, from being standalone to the Hadoop era to the cloud era. These are just evolutions, one on top of the another. And with cloud itself, what data engineers actually got was a capability to get compute, to get resources on the fly. Cloud computing really helped people to be completely away from managing and administrating services, and allowed them to focus on developing products and tools that are more relevant to the businesses. Rather than keeping the lights on, they were spending time on actually business value adding activities. I can give you one example as well, that in 2011, when I was setting up my own Hadoop cluster on premise, it took me around 4 days, 5 days to just set up the cluster, and another 4 or 5 days just to configure the cluster so that I can run one query. About 2 weeks is what it took me, and I was actually fairly proficient and understood how the internal workings actually was for Hadoop. However, with cloud, with HD Insights on Microsoft Azure or EMR on AWS, within 15-20 minutes, you have a full-fledged cluster available with you with default configurations, allowing you to immediately get started with. Likewise, cloud has also made it easy for people to not just spawn services on need, but also make sure that the utilization of those services is optimal, thereby bringing out more resources when required, and then again scaling down when it's not required, thereby keeping the business happy as well. So as long as a cloud platform is properly set up, data engineers are also happy because they have their tools to work on the requirements that they have from their businesses, thereby not pushing them or even allowing them to wait for IT, traditional IT, I should call, uh, to procure servers for them, and then they would get their hands on it. And just one case in point again here is that if we use the latest version of Databricks, with just a couple of clicks, we can move from CPU to GPU as well. Again, cloud actually enables that you can use different kinds of computes depending upon what the business problem is. Again, fit for purpose is the need of the hour, and cloud actually enables that.
Yeah, absolutely. And I think, along with the reduction in lead times and better for performance, I think where cloud platforms have definitely helped us is in terms of cost, right? Storage is so cheap now. It has really revolutionized how we store data, how long we can keep it for, and also in terms of, how we do our dimensional modeling and how we actually store different copies of data. Sometimes it may not necessarily be for the better, but it certainly has opened further avenues for us to consider, right? And cost becomes less of an issue.
Yeah, there is always this aspect of using a service and using a service properly, and
Yeah.
cloud is no different too as well, like you also called out. For an enterprise, there are multiple resources. One is human resource, where data engineers like you and me are actually working, and where we spend our time, and it's one of the costliest resources. Then there are compute resources, there are network resources, memory resources, and then there are storage resources. Storage resources might be the cheapest one. However, they also have one of the biggest inclinations to actually not be configured or not be used properly. The data model itself might not be kept right, and data warehouses might not be configured properly because the data model isn't right, or the data lake might become a swamp because either the data model is not fitting properly, or there is no data governance altogether. So, like you said, it's important to actually use these services, and as data engineers, while we work towards them, these are also ancillary skills that we as data engineers imbibe in our work, so that we are building applications or data assets, data pipelines, while we actually make sure that these assets can also be used enterprise-wide, and there is real return on investment that has been made on these resources, human resource, network resource, on the cloud that I just called out as well.
Yeah. So we do have a lot more to discuss, Anshul. I think let's look at some of the key outcomes of essentially this whole evolution of data engineering. But I think our audience must be eagerly awaiting our first giveaway question. So let's go to that first, and then we'll continue. Yeah, so here we go. Like I said, these are very easy questions. So the first giveaway question is, what are the 4 common sublanguages of SQL? But like I said at the start of the call, please do wait till the end of the webinar to send in your answers to octave@keels.com. But the question is, what are the 4 common sublanguages of SQL? Anshul, shall we have a look at how this evolution of data engineering has actually meant in terms of some of the key outcomes for us?
Yeah. Let's talk about them one by one. Let's look at the top left corner first, from proprietary solutions to open source. Uh, over the last few years, over the last couple of decades, I should say as well, people who actually, or data engineers who actually started at that time, used to use proprietary solutions like Informatica. IBM had DataStage, then Microsoft had SSIS. These were proprietary tools. These were drag and drop visual tools that actually allowed different data engineers to make sure that they can ingest the data or extract the data from different sources, ingest it, transform, and then load it, ETL, like we call it in short. They were actually supported by more proprietary solutions like databases, Oracle database, DB2. There was MySQL as well at that time too. However, the prominence was always towards proprietary databases as well. Now, from those solutions really at that time to today, where the information and knowledge on how to actually transform data or do ETL data is very, very freely available. There is no dependency, or I should say, a very, very limited dependency on the tool of the choice, and that dependency is really a conscious call. You use open source programming languages, you use open source libraries, you even build products and then contribute back to the community as well, so that there is higher collaboration, and in the future you get more products and more tools as well. You're not limited to a single product that was inventing at or providing features at a specific speed. You are now dependent, or your speed of innovation is actually in your hands. If you don't like, or if you don't see a product or a feature in the tools that you have been using, you are completely open to actually develop that on your own, start using it, and contribute back to the community too. That change in mindset of being dependent upon enterprise vendors to provide specific features and use those tools to actually gaining control on how you actually work, that has changed drastically from in the last few years when we look at the way data engineers have been working. Now, if you look on the right hand side of things, we just talked about working on premise and on cloud, and I'll not focus a lot on this point because we've already spoken about it. But again, with the advent of cloud, the cloud era actually allowed us to have our storage and compute decoupled altogether, thereby allowing us to control the storage layer and the compute layer separately. Again, allowing us to have different tools, fit for purpose tools for storage and fit for purpose tools for computing, or multiple tools for computing, multiple tools for storage. Again, a level of flexibility that is given to us, that is available with us in this era today, allowing us again a lot more control on how we want to build the solutions. Likewise, if I just continue and look at the bottom right corner where we are talking about different styles of architectures, there have been different architectural patterns over time where depending upon what the business need is, we actually either build data marts and data warehouses. These marts and warehouses were pioneered by Ralph Kimball, Bill Inborn, and a few other folks as well over time, and that those have been the Bible, the books written by and the philosophies written by them in terms of data modeling have been Bibles for data engineers in the last few decades on how would they be actually structuring their data so that it can be queried in an efficient manner for building dashboards and reports. That changed, I should say that got complemented with data lake architectures where you don't really have a fixed schema on writes. However, you have a schema on read a lot of times, or even you have a denormalized model where just because analytics is more iterative in nature and also requires is also unpredictable in nature, it requires data to be stitched together in white tables rather than multiple tables which are joined at the query time. Thereby, a different kind of an architectural pattern, a warehouse, a data lake. Sorry for that. However, when you actually combine, and another pattern that's coming out is combining a data warehouse and the requirements or the aspects of a data lake together to bring something out as a lake house, where you don't have to have separate systems. You can actually have a single system for both reporting and for analytics as well. However, these are just a few patterns. Think about data virtualization that has been in existence for quite a few years as well. That allows you to have a federation layer across all your underlying systems, all your underlying databases, all your underlying data stores. And from an end user perspective, there is a single system only. However, from an engineering perspective, there are multiple systems fit for purpose that are being used, that are being stored, that are being configured so that end user requirements can be filled in. These architectural patterns have actually been evolving over time, and for each of these architectural patterns, there have been specific techniques that have evolved over time as well. And as a data engineer, it's important for us to actually learn these, understand these, and be in a position to know that if there is a business problem, and if we have a pattern, which pattern actually applies to which business problem. That is a skill that comes with practice, with experience as well, and it's important to actually have that skill as well when we talk about data engineering and mastering data engineering over time. Now, all of these combined actually allows us faster business outcomes. Chamita earlier just pointed towards it as well, that where earlier with waterfall kind of project management and with the tools and the systems that we had, it used to take years to come out with some sort of an outcome that a business can actually utilize. That has shifted from years to months, and in a lot of cases where I've been working with enterprises, it has actually been shifting now to weeks. All of this is just because data engineers who are actually building and making sense of the data so that insights can be generated of the data. The data engineers actually have a lot of control now in terms of what hosting platform they use, tools they use, and with the availability of infrastructure and compute on burst, it just allows them to expedite their work. And with their programming expertise, they are able to bring in software engineering experience to the world of data, thereby codifying their assets and allowing the same code to be actually reused multiple times. And all these things together allow for decreasing of the end-to-end time from years to months to weeks.
And that's key, right, Anshul. I mean, a lot of everything that we do is essentially geared towards helping the business get some value out of the insights that we generate out of us collecting data for a specific business use case, right? So it's important that we ensure that we're not now looking at projects that span 6 to 12 months, but instead look at weeks, because otherwise by the time you get your platform out and running and create insights, those insights would probably be meaningless or near meaningless. So it's important that all these factors have come together to ensure that we are now able to serve our businesses better. We do have a stream of questions coming in, Anshul, and one is an interesting one around data privacy and specifically around GDPR. But let's take this question sort of at a higher level than just data security, right? Or data privacy. In terms of data governance, how has that changed over the last 10 years, and where does that kind of tie into what we're speaking about here?
Well, data governance is a parallel discipline of data. I've been calling out data engineering as one discipline, data governance as another discipline, and both data engineering and governance actually partner together to make sure that you don't only you're not only in position of actually making sense of the data, you are able to actually holistically manage the data. Let me give you an example here. When in an enterprise where data governance and data engineering are working hand in hand, you would see that there is clarity, number one, in understanding what the meaning of the data is, where the data governance work actually sets up standards and policies to define what the data should mean, and data engineers actually put in controls to make sure that there are validation checks to ensure that there is compliance to those standards and policies. Take example of data quality in this case. Data governance actually defines how the business looks at date formats. It should be YYMMDD, and data engineers actually apply those rules in their data pipelines. Likewise, metadata. Metadata is, by the way, data about the data. Data governance really defines what is the technical metadata, which means that in a table, how many rows are there, how many columns are there, as well as business metadata. As an example, what is the definition of a particular data element in business language? And what a data engineer actually gains from this metadata is that with this both technical and business metadata being available, a data engineer actually gets enabled, because now a data engineer will be able to find the data easily across terabytes and petabytes of data across the organization with the metadata itself. And as well as once they find it, they have the exact same understanding of the data as the business has. They know the exact same definition of how the business actually wants them to understand, thereby again allowing them to really work together and lean on each other, providing benefits to each other and working together. And that's where I was actually calling out partners. And there has been a cliched term that a data lake can become a data swamp. But really, when we actually look into detail of this particular cliche, Really, the big differentiating aspect is data governance. For our data lake, where there isn't any governance or limited governance, the data lake has a huge tendency to become a swamp. And data engineers actually struggle making sense of the data. They actually work, they have redundancy in their work, if I have to call that. And data governance is that discipline that really allows data engineers to work in a more efficient manner. And data engineers, in return, allow data governance to institute the standards and policies on top of the data so that those standards and policies are complied to, thereby them working together.
And that's key, right? Data engineers can't be just a consumer to data governance, but in effect, data engineers need to work alongside the data stewards to put together kind of the framework or the principles around data governance. And I think, you know, that's not just something that's relevant for data governance per se, but I think that's across the work that a data engineer does. It's important that we work alongside our business partners, and I think certainly from my experience, the most successful data engineers have been those who are able to actually bridge that gap between the technical and the business side of things. Now, along with these changes over the last 10 years, another area that has certainly seen a lot of innovation and development is sort of in the different tools that are available to kind of do the same thing, right? And by the same thing, I mean so many different tools to do ETL, to do visualization, data governance, etc. And also on top of that, with the popularity of tools like Python, you can actually build your ETL in something like Python as well, right? So in your mind, Anshul, what's the best way to go about this? What's the best way to go about selecting the right tool for the right operation?
Yeah. This is really the need of the job itself, and because in this era we've been talking about that there is a problem of plenty too. That a lot of tools are available, a lot of platforms are available, and really, how do we go about finding the best set of those tools for the right problem? And the way I actually go about is I stay business driven again, business problem driven to be more specific. For a particular problem, what are the functional requirements that the business problem needs? If the business problem is actually ingesting petabytes of data from 10 different sources and then doing complex transformations and then just keeping that data at a single place, there would be a different set of tools that I'll be using. However, if the requirement is really to ingest data in real time, event by event, and actually process or or do a transformation actually on each event, making sense of each event, I would actually use a different set of tools. Really, whatever is the business problem at hand, I convert that business problem into what it would look like in a technology sense. I gave two examples there, and while I actually do that, I actually take another two lens from an enterprise perspective. Number one is the capability that I have in-house. If I am the only one who is working, it's an easier decision. However, if I'm taking that decision for an enterprise, or if I'm taking the decision for my team, whether that expertise is available for that tool already or not, or if not, then can that be actually embedded in my team in a quicker fashion? I actually stage my framing or the set of tools actually according to that decision. And while we are working in an enterprise, cost is definitely an important aspect. And this cost could just be a license cost if it's an enterprise product, or it could also be a cost of maintaining the products and the tools. With open source, there are a lot of advantages. However, there are other aspects that we as an organization need to also ensure. And the case in point here is to, if we are using open source technologies, how are we ensuring the security of those open source libraries itself? How are we maintaining those products that are being made with those open source libraries too? That's also a cost. There is also a cost of maintaining these pipelines and data assets. I also look at that if maintenance of a particular tool or a product that I need for this business problem requires a lot of maintenance. Again, it's something that goes into consideration. that cost needs to be taken up, and thereby actually coming up from a huge list of candidate tools to actually a set of final couple of tools, and then actually taking a decision because that is how I will be able to make sense of all the options that I have in hand. So I start eliminating, and then at the final leg, when I have just a set of candidate tools, I actually stop eliminating and do a selection between 2 or 3 final set of tools.
And to be honest, being able to select a tool is a luxury that we data engineers don't always come across, right? Most often than not, when we join projects, the tools would have been kind of decided
Selected.
before. Yeah, selected already. And I think it's about keeping an open mind, and this is where the importance of what we stress at the beginning, being able to having a good grasp of the principles behind these tools is important, which means that no matter what project you walk into, you'll be able to pick it up straight away because you have a good grounding in the principles of how these tools work. We've got one question, Anshu, with regards to Python libraries. Are there any particular libraries you would say are essential to a data engineer?
Well, there are a lot of libraries, and it's also an experience-based question that what all data engineers have experience with what libraries, rather than actually saying that which libraries are essential to a data engineer. I would really want every data engineer to explore and find out their own set of libraries that they are comfortable. However, libraries from a data engineering perspective that are fairly popular, yes, there are quite a few of those libraries. Take example of a library called Pandas. That library allows a data engineer to work, to transform with the data itself, to join them, to make sense of the data. Likewise, there are other libraries that are very, very specific to specific purposes. If the data really is in time series, there are specific libraries for that. If you are actually building pipelines, there is a library called Kedro that actually Quantum Black maintains that allows you to build pipelines in a configuration-driven manner. So there are a few libraries which are fairly popular, and I would really urge budding data engineers and data engineers who are looking for a standard set of tools to standardize their own work to actually start with these libraries. However, do not limit yourselves to these libraries. Explore more, identify what other libraries are being used, and then actually also take a call according to, like I was talking about, the business problem that you have, and also if you are using it for your own purpose versus your enterprise. All of those aspects also still hold true at this granular level of identifying the right library for the work at hand.
Yeah, no, that's some very good advice. I know we were meant to finish at 7 p.m., but given that we started a bit late and we've got a few more questions that I really want to go through to do justice to the participants who've been kind enough to submit them. So I would like to go maybe say 5 minutes over 7. But just before we continue this discussion, Anshu, shall we go to our second and final giveaway question, and then let's continue our discussion?
Absolutely.
So the second giveaway question, again, like I said, they're very, very simple. Name the tool built and used by Facebook for their big data querying. Again, name the tool built and used by Facebook for their big data querying. Please do send your answers to octave@keels.com, but please do so at the end of the webinar. Just taking up the discussion where we left off, Anshu, in terms of well, we talked about Python, we talked about the different libraries and how we go about tool selection, right? Let's delve a little bit into the different styles of architecture, right? Because again, this is something that has gone through a lot of different changes over time, and certainly something that affects our day-to-day work, right? So we're showing here sort of a mini evolution from a data warehouse to a data lake to a data lake house, right? In the interest of time, if we kind of just concentrate a bit on the data lake house, because I think that's what a lot of us would be unfamiliar with. What are your thoughts on this? Is this something that you've given a try?
Yes, absolutely. And you're right. We briefly touched upon it in the previous section. Let me just provide some more details on it, and I'll stay conscious of the time as well here. Really, this is about different patterns that have evolved over time when it comes to engineering as a discipline. In late 80s, late 90s, data warehousing, building data marts was the prominent pattern of actually storing the data and making sense of the data, structuring the data when it was stored. Dimensional modeling, star schemas, and snowflake schemas were the primary ways of actually storing the data when it came to actually analyzing the data, and when it was behind transactional systems. First normal form, second normal form, a lot of times third normal form was the way actually storing that data, and which is what was the prominent pattern of storing the data. Over time, with the need of the businesses, from structured reporting, the needs of the business actually went from structured reporting to exploratory analysis, predictions, and prescriptions. And for that, these patterns of actually storing the data actually slows the work down. What actually evolved from these schemas or these data models from being very, very centric to dimensional modeling, actually they moved uh, from dimensional modeling to actually complementing it with denormalized modeling or data modeling techniques, where data was not structured when it was being written. Most of the places, be it HDFS, Amazon S3, Azure Blob Storage, these are all object storages where every data point is actually stored as an object and then made sense of it while the data is being read. So from having a scheme on write, actually the evolution moved on to scheme on read. And this schema, while it was getting applied on read, really benefited when all the data was combined together in wide denormalized tables, thereby reducing the number of joins and making it easy for data engineers and data scientists to actually read the data together. And this combined with different data formats or storage formats, you would have heard of formats like Avro, Parquet, ORC, specifically ORC and Parquet have been used quite a lot in the recent times because they are columnar storage formats, thereby allowing you out of 100 column file, just pick up 2 or 3 columns and only that data is read as an example. All of those are parts of the architecture evolution that has happened from the data warehouse era to the data lake era. And now there are different organizations that are trying to federate and combine both of them as well, making sure that the kind of data models that we use, the kind of storage formats that we use, it allows for capabilities both for structured reporting as well as exploratory analysis that is required for analytics, and thereby coming or coining up this marketing term of data lakehouses. Data lakehouses actually allow for that. However, again, it's a different avatar or a version of data virtualization where you have multiple systems, multiple stores, and from an end user perspective, you have a single interface to actually work towards it. But every technology is different, and lakehouses now is moving in a direction where these architectural patterns are now converging together. Thereby, from an end consumer perspective, you have a single system where you are doing both reporting and business intelligence work as well as analytical work. And likewise, this transition will continue, and it will go in a direction where, again, whatever is the business need, whatever is the problem with the current lakehouse architectures, that would be solved with the future architectures. There will always, a necessity will always push to actually do innovation, and thereby allowing us to learn another product, another architectural pattern. What is core in all of this is that none of these patterns that we've called out are going anywhere. They just get accumulated, they get actually evolved from one to another. And as a data engineer, it's important to learn them because until unless you know about these patterns, you will not know when to apply which one for which kind of a business problem. And that's a core skill for data engineers.
Completely agree. I do want to ensure that we finish at 5 minutes past 7, but I also want to take up very quickly take up a question that seems to be rather popular. What exactly is the difference between a data engineer, scientist, and analyst? What's your one sentence answer to that, Hansha?
It's very difficult in a single sentence. However, I'll try my best. A data engineer is the one, if like, in fact, I'll take a step back. working with data is a team sport. A data engineer is the one who actually connects different systems in an organization, captures that data, and makes that data available in a way that is consumable. That's data engineer, or the more core foundational skill of a data engineer. Once the data is structured so that it can be consumed, a data scientist or a data science domain or discipline actually picks up that data and uses complex algorithms. These algorithms could be mathematical algorithms that actually make sense of the data and provide insights. They derive insights from the data that's actually generated by the business itself. And an analyst is someone who works along with both engineers and scientists, working to make sense of the data itself. They explore the data, generate reports, not just to enable data engineers and data scientists, but also primarily are business facing. So if a business leader requires the top 10 most performing products in their business, a data analyst could actually build those reports and make those reports available to the business. Enabling both the data engineers in a similar fashion in understanding, allowing them to understand what the data is, as well as building these reports for the business as well. I took more than a sentence. However, that was a synthesis that I think demanded at least 2-3 sentences.
No, I agree. I think that was a few more than one sentence, but I think that was still very well put together, and I'm sure the audience member will thank you for that. And I want to thank you, Anshul, for taking the time to be with us and to share your experience and insights. I hope that the audience has learned or heard something new today, and a big thank you to them for making the time to join with us this evening. And we look forward to welcoming you to our next webinar, where Rajita and Paul will be discussing data science on the 1st of December. It is also at the next webinar where we will announce the winner of our Microsoft giveaway. Thank you very much for joining, and have a good evening.
Thank you. Stay safe.
Thank you.